Hello, 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 hello. It must be 2 hours UTC because it's time. It's time again for Astronomy Daily Live. This is a daily live stream. We get together every single day and gather together, circle of friends, and we talk astronomy for an hour, hour-ish or so, sometimes a little less, sometimes a little bit more. Hope everybody's doing well. Hey, hey, hey. It is 2 hours, 1 minute UTC on the 26th of February, 2018. You can call me Cosmic, and here we are again every single day. Isn't this awesome? I like doing this daily thing because it's just fun. And yeah, I don't really feel as though I have to, pack a lot in or try to overwhelm or, do too much because, oh no, I'm only doing this once a week or once a month or a couple of times a week, doing this every single day at the same time, same place. Hope everybody's doing good. Hope everybody had a great day or a great evening wherever you are on the planet. Um, this is Astronomy Daily Live. This is a live stream. Hey, hey, hey. Glad everybody could stop in. Those of you who are coming in live, welcome, welcome. Come on into the circle of friends. Let's talk astronomy for a while. Um, if you are catching this later on and not live, uh, watch away. Hope, uh, yeah, hope you enjoy yourself for sure. Uh, I know that this isn't a good time for everyone, so yeah, maybe at some point that can be remedied in some way. But for now, 2 hours UTC is a good time. Um, it's sort of an arbitrary choice. Um, where I am located on the planet is in southeastern Arizona in the United States, and that puts me in a time zone called Mountain Standard Time, and I am 7 hours behind UTC, Coordinated Universal Time. So when it's 2:03 UTC here in my location, I have to subtract 7 hours. So it's 2:03 UTC on the 26th of um, February, but where I'm located, it is 7:03 p.m. Mountain Standard Time. So on the 25th of February. So, you know, the measurement of time can be a confusing thing, but it's a hurdle that anybody who wants to get into astronomy has to overcome. You have to endure, and you have to overcome, and you have to wrap your head around the concept of time, because the concept of time and measuring time is, I would say, probably the most important thing um, in terms of astronomy to try to understand. So, the sooner that you can understand that, the better, for sure. So, I'm going to get my little doodah here going. Let's see. I like to watch the live stream on my smartphone so I can see how silly I look. Always like to do that. And over here on my Linux machine, I like to uh, pop up the chat, the YouTube chat. Also, you'll notice in the description below that I have a link to my Discord server. I've been a little active on that today. Uh, just because that's how it goes. Let's see. So I want to go over here. Do I want to go over here? Yeah, I want to go over here, and then I want to go here. There's just so many steps. There's so many steps. There we go. So glad to see everybody live in the chat. I'm going to pause the live stream on my Linux machine and wait for the chat to come up. And then I can pop the chat out. And that will be that. Dun, 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 dun. Uncle Bill is in the house. Bob Dog is in the house. Hey, hope everybody's doing well. Bob Dog, I hope you're staying warm up there. I guess if you're along the coast, it probably isn't uh, as nasty as it could be. But of course, there are certain hazards along the coast too. But wherever you are, I hope you're having a great time, because that's what it's all about. So yeah, glad you're here. Hey there, Tom. Nice to see you coming in. Glad you could stop by. And I say this often, don't feel as though you have to come in every single day. That's kind of the cool thing about having a daily live stream, is that, friends can come and go as they please. And if there's um, something else, that you would rather be doing during this time slot, if there's another live stream that you want to um, watch or participate in, go for it. Go for it. There's a lot of room for all of us, and I don't feel any sense of competition at all. The topic of astronomy is huge, is huge. So yeah, if there are other shows that you like to watch while um, this one is going, you can either switch to those, come back to this one from time to time, or do what um, um, Uncle Bill does, and he does it ninja style, right? He's got like 8 screens up, and he's watching them all at the same time. So that's incredibly awesome. So yeah, we're we're just a group of friends, gathering together. Um, Whether you're new or you're a pro or anywhere in between, you are welcome here. Make sure to chime in, say hi, whatever it is. Contribute to the conversation. I'm not the only one, that can talk here. So yeah, when it's a group of friends sitting around, conversation can go pretty much anywhere. So the drink of choice tonight is is hydrogen hydroxide. It's my go-to chemical, HOH. It's both an acid and a base, and yeah, it's probably one of the most amazing molecules in the universe. And we find we find this shit everywhere, everywhere. So cheers! I'm glad it's here. Ninja mode is off today. Uncle Bill, what's wrong with you? Are you feeling okay? Are you feeling here? Let me feel your forehead. Okay, I don't know. I don't know. A little quiet, huh? Well, it is nice to relax once in a while, and you know regain your strength a little bit. So yeah, cool. So uh, if the crowd, really doesn't have any kind of conversation, I've I've got lots and lots of topics right right back here in my back pocket. Just a big, huge stack of them, and that's the cool thing about um, um, astronomy is that we're having a conversation about everything. We can talk about everything. We talk about the universe. So yeah, there's lots to talk about. Um, always, always something new, always something old, always something in between. There's just there's so much to learn and so much to find out. And being a scientist, I am intensely um, um, curious about pretty much everything. Pretty much everything. I want to know how and why and where and when and who, the whole the whole thing. So what I rely on is a process that is called the scientific method, and this is a fractal process in that the output of it gets sort of fed back into the input, and then it's processed again, and then the output of that goes back into the input, and it's processed again. It just goes around and around and around. Science is not a beginning and a middle and an end. Science is a process. So anybody who says we're done with that, no, probably not. Probably not. Um, you know, maybe you can be fairly certain about things, maybe, but are we ever done with it? Nah, not at all. So I'm going to share my screen here and just show you. I think I grabbed this off of Wikipedia. So let's see. What am I doing here? I'm going to do this one. Dun, 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 dun. So there it is. Scientific method as an ongoing process. So as you can see, there's really no beginning or middle or end here, right? It just sort of goes around, goes around, goes around. You can pretty much start anywhere in this, and you'll eventually come right back to where you started from. Um, a lot of times, you know, we'll make some kind of observation, right? What do we see? We're sitting around, looking around. Maybe we're bored, and so we start to use the senses that we have, to make um, 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 observations about things. So, what do I see? What do I hear? What do I experience? Those kinds of things. And it's like, oh, okay. Then you can sort of go on to, the next process. It's like, huh, I wonder why that's happening. Hmm, I don't know. Let's think about, why I'm seeing a certain thing going on. And you think about that for a while. You let it cook, go to sleep, sleep on it a little bit, wake up the next day, you think about it a little bit more. Yeah, whatever. After a little while, maybe you start, to uh, make some guesses. It's like, well, okay, well, maybe I'm experiencing these things because of whatever, right? It's like, okay, well, now I've got some guesses, right? You formulate some hypotheses, as they say, and then you say, okay, well, if if I'm right about that, then I should sort of expect to see this thing happen. Or if I'm wrong about this, then I should see these kinds of things happen. Every every guess does need to be falsifiable, right? You have to find conditions under which you can show that it's false. So if you can't do that, then it's not really a hypothesis. So then you go and get some data to test your predictions about what you think the hypothesis is about. And you can get into this little sub loop in here, right? Where you just loop around like this. And this is a um, iterative process where you're just trying to improve upon this sub process here. And once you think you're doing pretty good, then you can um, um, develop sort of a general theory. And then what you do is you start looking around again. And then the whole process starts over. So, this is science, and this is what scientists do, or at least should do. Um, Sometimes scientists don't, but really, really should. And when you read papers, that are written um, by the pros, you will see that that um, um, the structure of the papers is generally like this, right? Where they sort of lay out what they've experienced, what the history of the problem is, what they've noticed, blah 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 blah, and then they'll be like, okay, well this is what we're going to do to sort of test our guesses, and then they go through the process of collecting that kind of data, processing that um, um, data, to remove all kinds of systematic things that might confuse things, uh, and then you know they present their results and they draw some conclusions, and then it's up to somebody else, to take those and run with them, and it just goes on and on and on and on and on. So very, very awesome. That is the scientific method. Cheers. Now, this live stream is a very casual and fun um, discussion of astronomy, but uh, at, at least, you know, for me, I'm going to be extremely skeptical of pretty much everything, but I'm also going to be completely open minded as well. So, new ideas or strange ideas or old ideas, um, those are all welcome here. And we can talk about them for sure. And I don't, as a scientist, I'm not going to throw things out just because I think that they sound silly, or don't match what we're so sure of, or anything else. I'm not into that. I'm into science. And so when there's some kind of, you know, sort of strange sounding um, 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 observation, that somebody has made, and they develop some theories, I'm going to take a good hard look at that for sure. I'm going to run it through this grinder, right? This is the mill, right? This grinds things up into fine particles, and yeah, we take a look at them. But be open-minded. Be open to the possibility that our perspective is so limited, and I mean, I already know as a scientist that our senses are infinitesimally limited. We can't see all there is or feel all there is. We can't even know a fraction of a percent of that. So, extrapolating out and saying this is how it is, I can't accept that. So, I want to be open minded about things for sure. And that just feeds curiosity and feeds um, uh, um, um, inquiry. Uh, it motivates me to want to dive into things really, really deep, and try to convince myself one way or another that something is either right or wrong or true or false. Those are absolute things that are hard to hold on to. They're slippery, but yeah, who knows? Who knows? So that's what this show is all about, and it has to do, with the topic, a very, very big um, topic of astronomy. So, and this particular science, it looks at pretty much everything, right, from the subatomic all the way up to the cosmological, the whole thing, and from the the longest wavelengths that we can detect to the shortest, and everything in between as well. And also in terms of time scales, right? We like to look at things that happen very, very fast, and we like to look at things that happen really, really slow. So it's everything. It's everything. So, yep, hope everybody's doing good tonight. What I wanted to do, I guess, was I wanted to try to confuse you even more with these celestial coordinate systems. Uncle Bill had a great suggestion. Was it today? Yesterday? I don't remember exactly, where he suggested that I run this program called um, Stellarium, which is it's sort of like a planetarium um, program that it just allows you to see the sky. You can identify objects. You can run time forwards and backwards. It's an awesome, awesome, awesome tool, and it's free. It's free. It's open source. So a programmer like myself can actually get into the source code, um, and not only see how it all works, right? I can look at all the formulae, to predict where Mars is going to be on a certain date at a certain time, where all the satellites are, just all of that. But I can modify the code, and I can do my own thing. And if it's really, really cool, I can probably, I would think, um, um, send that into the solar the um, um, stellarium uh, group, and they may um, put that code into the main um, distribution. So yeah, it's very, very cool. However, having said all of that, um, uh, for some reason, when I tried to run Stellarium on this sad laptop that I have here running Windows 7, 64-bit, it completely barfed on me. So it wasn't able to run. So what I did instead is on my Linux machine, I just made some pictures. So this is sort of a typical screen that you will see, and the details here aren't extremely important. I sort of chose this. This is the sun, of course, and as you can see, it is setting in in the west. So this green line here is the horizon. Okay, so everything outside of this circle would be below the horizon, right? And everything inside of this circle would be above the horizon and, of course, visible in the sky. So just marking the cardinal points here. So here's west, here's north, here's east, here's south. Okay, and as you can see, this image was taken just as the sun was setting in the west. You can see that Mercury and Venus are east of the sun now. They're evening stars. Here's the moon. Here's Orion. You can sort of see Orion here. Here I can zoom in a little bit. As I said, the details here really aren't that important, right? But here's Orion. Here's Orion's belt, Sirius, blah 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 blah. Not really important. What I want to show you is more lines. So as I was saying the other day, there are basically 4 different celestial coordinates systems that astronomers will use. First one is called the altitude azimuth system. And so what this program allows you to do is actually show those lines on the sky. So I'm going to do that. So this is going to be the altitude azimuth system. So hopefully you can see that okay. What you see here is sort of concentric circles, and I'm going to look on my live stream on my smartphone to make sure that that's relatively easily visible. Let's see, there's a little bit of a delay, so let's see if I can. I'm just going to wait till I can turn that on so I can make sure that it looks okay. Ooh, there's quite a delay today. Quite a delay. Not seeing it yet. Or am I? Oh, I am seeing it. Okay, it's pretty faint. Okay, I'm going to have to work on that a little bit. But the altitude azimuth system is basically sort of a local kind of a thing. So the altitude of a star or an object in the sky is defined as the number of degrees above the horizon. So as you can see here, it goes from 0 degrees, which is the horizon, 10, 20, 30, 40, 50, 60, 70, 80, 90. 90 degrees above the horizon is what's called the zenith. That is straight up, wherever you are on the planet, when you're looking straight up, 90 degrees from the horizon, you are looking at your local zenith. So that's what's called altitude. Okay, altitude. So it's just defined as the number of degrees above the horizon, your horizon. The other number is called azimuth, and azimuth is measured if you take the zenith point and draw a line from the zenith point to the north. Okay, way up here. I don't know why that's moving around like that. Okay. The azimuth is the number of degrees going west and going around like this from north. So azimuth starts at 0 degrees when you're looking north. It goes to 90 degrees when you're looking west. It goes to 180 degrees when you're looking south, 270 when you're going east, and then almost to 360. But of course, as soon as you hit north again, you're going to be at 0. So it goes all the way around this way, 360 degrees. And that's why hopefully you can sort of see, the concentric circles here. So azimuth goes all the way around. It has nothing to do with the horizon at all. So I can be looking at an altitude of 80 degrees and an azimuth of 90 degrees, and that would mean that I would be looking 10 degrees west of my zenith. Hope that makes sense. So this is sort of just a local kind of a thing, a local coordinates system. Cheers. So another coordinate system that is used, and this is the most commonly one used, is called the equatorial coordinate system. And I'm going to go to the next slide here. Boink. And you'll see a bunch of blue lines. They sort of splay off this way and sort of splay off that way and spread around and who knows what, right? But as you can see, there's a point right here where, all these circles are sort of concentric around that point, and then all these other curved lines sort of all meet at the same point right there. Now, what that's called is the north celestial pole. And I don't know if you can see it or read it or not. You probably can't, but way up here it says 0 degrees. That is what's called the celestial equator. And that's that line right there. So what this basically is if you took the lines of latitude and longitude on the Earth and sort of extended them out onto the sky, this is what you would see. And so these lines of longitude are what's called right ascension, and these lines of latitude are what's called declination. So at the north celestial pole, that is defined as a declination of 90 degrees, positive 90 degrees. Now, below the southern horizon, way below, like way down here, is the South Pole, and that's at a declination of negative 90 degrees. So, and the celestial equator, of course, is just like the Earth's equator, and that's at a declination of 0 degrees. And the reason why it's curved, Uncle Bill, I think you're right. I think you are right. My my apologies. That's exactly right. In the alt-azimuth system, as as if this isn't confusing enough, right? And then I go and just mess it all up, right? So azimuth goes towards the east. So this away. So 0, 90, 180, 270, like that. Yes, you're exactly right. Thanks, thanks, thanks. All right, well, cool. So as I said, this is sort of the most commonly used um, um, coordinate um, system used in astronomy, where we have sort of our east-west lines. These lines of longitude, I guess if you want to call that, but um, we astronomers call it right ascension. And then these lines of latitude, which are these guys, which is called declination. And we have a North Pole and a South Pole. So we still have a zenith, right? We still have a zenith, but that is in a different um, coordinate system. Yeah. So interestingly enough, and I don't know if you knew this or not, but the altitude of the North Pole here is exactly the same as your latitude. So if you look at this, you can see that my latitude is 10, 20, 30, 32-ish or so. And that's exactly right. That's exactly right. So that's kind of cool. And also, let's see, the, is that right? Yeah, how can I explain that? All right, well, I'm going to move on. So, yeah, this is sort of the most commonly used coordinates system in terms of giving um, positions of things in the sky. So if you look up the position of Betelgeuse here, you will get a right ascension and declination for that star, et cetera, et cetera, et cetera. Okay, so there's two more coordinate systems that are used. One has to do with it's sort of in relation to our solar system, and that is the ecliptical or um, ecliptic coordinate system. And as you can see, the sun is at an ecliptic angle of 0 degrees, and it's always at um, 0 degrees. In fact, if you sort of imagine the Earth going around the sun, um, if you can um, define that as a plane, as like a very, very flat plane, that's sort of what this line is. Now, the reason why it isn't a straight flat plane is because this is being projected onto the sky. So everything gets distorted when you do that because we're sort of seeing the sky as a sphere instead of a flat thing. So as you can see here, there's also a north pole to this one right there, and a south pole, which you can almost see here on that one. Now, all these numbers, as far as I know, are measured in degrees. So the ecliptic coordinates, both sort of left and right and up and down, are measured in degrees. So see, here's 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So again, it goes from 0 to 90 to the north, and then 0 to negative 90 to the south. And I think looking around, yeah, so looking at these concentric circles, it pretty much does exactly the same thing as the other one did, and that is it starts at 0 degrees going north, and then it goes 10. Let's see if I can get some numbers here. I'm not seeing any numbers. 225, 270. Oh, I'm going to zoom in a little bit so I can see these numbers maybe. Talk about being prepared. Gee whiz. 270, 240, 225. Oh, I don't know. See, it's confusing to everybody. But it does go all the way around, for sure. 0 to 360, all the way around. This coordinate system isn't used as much as on the equatorial system. Pretty much, if you're into planets or solar system type of things, then this coordinates system would be most useful. But usually it's not used that much. It sort of has a much more specific use. So yet another coordinate system is what's called galactic coordinates. And as you can already see in this image, here is at least a slice of on the Milky Way. And as you can probably guess, the galactic coordinate system has everything to do with the position of our galaxy relative to us. So let's go on to the next one. And there it is. So as you can see, hopefully see relatively well. I got to work on these lines. I got to get them a little thicker, I think, because they're kind of hard to see on the screen. But here is 0 degrees galactic latitude. And as you can see, it's going right through the center of the galactic plane. And then you can move north or out of the galactic plane and eventually hit the North Galactic Pole. And then you can go this way out of the galactic plane, and you'll eventually hit the South Galactic Pole. So you can see relative to our solar system, I'll go back to this one again, right? The galaxy is tilted, or if you want to put it another way, relative to the galaxy, our solar system is tilted. So we we aren't lined up with the plane of the galaxy at all. We're at an angle here, right? You can sort of see that. Whoop, we go from that where it's sort of going this way to sort of going like that way. See, so there's a funny angle here. So we're turned all around, all around. And again, the galactic um, um, coordinates system isn't used all that much unless you're talking about galactic kinds of things. Um, but yeah, not used a heck of a lot. So then finally, just to completely confuse you totally, here they all are on one screen. So yeah, we humans sure like to complicate things, and we've we've done a pretty good job, you know, making the sky pretty complicated. So, but these are all different ways of measuring things. It's just a measuring stick, and really, my favorite is that one where there's whoop that one because there really are no lines in the sky. Absolutely none. There's just stuff. There's just stuff out there. So I'll come back to this. I will, definitely work on refining definitions and trying to make this clearer uh, as time goes by. But for now, I think that's where I'm going to finish off with that. So, cheers. I guess what I wanted to do now is let's see, I can to go back to this for the moment, which means I have to stop slouching again. And guess what I wanted to do was maybe go over to archive.org, and the latest and greatest papers are probably out because it is the 26th of February, which is a Monday. So let's just go over to archive.org here and see what's new in terms of astronomical research. All right, so I will, now that I'm over there, I will share my screen again. I like sharing the screen a heck of a lot more than you just having, to look at this all the time. So archive.org, I can't say enough about it. It's totally, totally awesome. These are papers that have been accepted for publication, but haven't necessarily been published yet. They will be, but as soon as they are accepted, then they can be put here for anybody to grab and read. And not only does the site have all the astronomical stuff, but they have all kinds of physics, mathematics, computer science, biology, finance, stats, electrical engineering, um, economics. These are all the latest and greatest papers on all of these topics. It's an amazing resource to have. And top of the list, rightly so, is astrophysics. So if you just click on new here, we will get the latest and greatest bleeding edge research, new submissions from Monday, 26 Feb 18. So these have just come out. These have just been accepted for publication. And let's see if there's anything interesting here. The really cool thing that, at least one of the cool things about these papers is that I sort of see them as um, um, jumping off points. Uh, uh, yeah, Uncle Bill, I totally agree. I definitely need to work on the presentation of that a little bit more. Get get my facts a little more um, complete, description a little better, and yeah, see if I can do some kind of a live thing. More um, um, dynamic and all that. So, hey, this is a ongoing process, and I'm not going to sweat it too much. My goal is to always get better. So need to start somewhere and go from there. So yeah, and with your help, that will be done for sure. So I need all you guys, to point out um, all kinds of things, that I'm going to miss because I know that you are watching. So these papers, I sort of consider them as nice jumping off points. So, you can pretty much choose any of these things. Um, and, you start to read it and it's like, oh, what's that? And so you follow that. And then on that path, it's like, oh, what's that? And you follow that path. And you just keep going and going and going and going and going. And it's really awesome. So you can pretty much choose a random paper and just learn an enormous amount of stuff. And you know, if the words or the mathematics um, are too confusing, just look at the pictures. Look at the description of the picture, and go from there. Got to start somewhere. So let's see, detection of a millimeter flare from Proxima Centauri. Well, we know that Proxima is a pretty active star that that does flare up. So each of these papers has what's called an abstract, and that's just a very brief description of the entire paper in a very condensed form, where they lay out what they did, what they observed, what the results were. Done. So it's kind of a really nice way, you know, to see what the paper is about without having to read the whole thing of an abstract. And usually they are. They're usually very abstract. Learn keyboard shortcuts to switch around easily. Yeah. There. Oh, that's what I really like about life in general. There's always something to learn. Let's see, signature planetary mergers on stellar spins, measuring scale dependence and shear, super solar metallicity stars in the galactic center nuclear star cluster. Huh. Okay. URAT. URAT. South parallax results. Okay, so it looks like they are measuring distances to nearby stars using the United States Naval Observatory Robotic Astrometric Telescope. That's kind of cool. So they measured, the distance and motion to 916 nearby stars. That's cool. Always nice to know how far away things are, because if you know how far away things are and you make an observation, it's like, okay, well, then we sort of know, how intrinsically bright they are. And if you know that, then, you can make all kinds of inferences about what is going on. Dimensionality and integrals of motion in the TRAPPIST-1 planetary system. Newton eyes on K2-3, a system of 3 likely sub-Neptunes. Cool. Look at all these authors. Plus 9 that aren't shown. They ran out of room for the authors. That's pretty funny. See, they're looking at molecules out there. That's very cool. Pretty big molecules, too. Pretty cool. H2 regions on the gas content and efficiency of AGN feedback in low redshift quasars. Woohoo, that's a mouthful. Properties of electron acceleration, chaotic excitation, and tidal damping in the GL876 system. So GL876 is an M dwarf star, so it's a very, very small, cool star, closest known to harbor a multi-planetary system. Very cool. Direct multiplex imaging and spectroscopy of an exoplanet with a solar gravity lens mission. Whoa, crazy stuff. That's what I like about science, though. It is crazy. Yeah, I think my guess is in the Proxima Centauri paper that we were up here, that they were seeing a flare in millimeter wavelength light. Let's just go back and look at that. Wow, did I? Okay, here it is. See, so the cool part is that all these, you can click on the PDF and you can actually get the paper itself. Dun, 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 dun. Detection of millimeter flare from Proxima Centauri. So we present new analysis of ALMA, 12 meter, and ACA at 233 gigahertz. His analysis revealed that the star underwent a significant flaring event during one of the observations. So yeah, most likely that event was probably also seen at other wavelengths. That's my guess, but they were watching it at the time, so that's very cool. That's very, very cool. The event lasted for 1 minute and had a peak flux of 100. I think that's millijanskis. So I can't claim to know how that converts, or if that's a lot or if that's a little. But they do say, that it was 1,000 times brighter than what the normal star is. So that's pretty cool. Steeply falling spectral index. Not quite sure what that means. ACA observations do not show any quiescent excess emission. We conclude that there's no need to invoke the presence of a dust belt. Okay, all right. We also posit that the slight excess flux density observed in the 12 meter observations compared to photospheric flux density. All right, so as I say every single time, there's a couple of things that I like to point out, and that is all the references. The references are ways for you to learn more about, a particular thing. So it says low mass, i.e., M type stars are the most common stars in the galaxy. And then there is a reference. So if you were to look up that reference, it would talk about the fact that these stars are the most common and sort of expand on that. So it's all these guys have to say is that, and then it's just done. And if you want to know more about that, you go to the paper. And that paper is, um, um, I'm going to have more references, and you can follow those, and then follow those, and follow those. It goes all the way back, all the way back. The other thing that I like to do is I like to go right for the pictures. So as I said, the scientific method should be used here. So the introduction just sort of lays it out, right? These are the observations that we made. This is how we conducted the observations, and this is how we did the analysis of the data, and these are the results. Let's see, detection of millimeter emission from Proxima Centauri. Okay. Left, natural weight images for all observations combined along with each observation imaged separately. Okay. Let's see. ACA observations. So yeah, they use two different instruments. One is called ALMA, ALMA, and the other is called ACA. We looked at both of those. 13 observations with ACA between the 21st of January 2017 and March 24th, 2017. Okay, so it took them, from the time that they collected their data to this paper coming out was a whole year. So most likely, these guys have sort of moved on, to other things. And the work that they are doing now, you're probably not going to see the results of that for another year. Oh yeah, look at that. So here it is, sort of, quiescent, right? And that's a flare. Wow, that's pretty awesome. Pretty bright. Look at that. Boom. Very, very short. They said that this lasted about an hour. Look at that. There seemed to be, sort of another flare here as well. Maybe a smaller one here, shorter, but then a big one. Boom. Very cool. Very, very cool. Okay, so here, they sort of spread it out a little bit. So this is the same as this little bit here, just sort of spread out in time so we can see the shape. And that shape, tells us a lot about what is going on there. You see how it sort of brightens up really, really fast, and then it lingers for a while, and then look, it just slowly decays like that. So that tells you a lot about what is going on there. I don't know what these other plots are. Polarization. Yeah, I'm not going to get into that. Then they have a discussion, of course. Nature of the detected stellar flare. Proxima Centauri is known to undergo frequent X-ray flares, but now they've seen it in the sub-millimeter. That's very cool. Stellar flares are typically associated with magnetic reconnection events. Such late type stars such as Proxima Centauri are fully convective and have high surface magnetic fields. X-ray observations suggest that Proxima Centauri's coronal flares are similar in temperature and density to those of the sun, our sun, while also um, exhibiting the Newport effect. See, what the hell is the Newport effect? Oh, look, there's a reference. If I want to find out about um, what that is, I can go to the reference. Very, very cool. Very, very cool. Yeah, we astronomers like to flip wavelength and frequency, and there's a inverse relationship there. So it you know as with um, um, coordinate systems, we astronomers like to confuse things. We're pretty good at that. Why have one if you can have four? Why have um, um, one way to measure wavelength if you can also have frequency too? So yeah, constraints on dust emission. Conclusions. We present new analysis of ALMA. During the AC observations, the star underwent a significant flaring event, 100 millijanskis. I assume that's a lot because it says it's 1,000 times brighter than um, normal. Now, just imagine for a moment, okay, if an event on our sun occurred that was 1,000 times brighter than the sun itself, that would be pretty exciting, I would say. So yeah, that's not necessarily a place that you want to spend a lot of time being near to. So yeah, any kind of planets or anything, are pretty having they're probably having a pretty rough time, I would say. There's all the references. Very, very cool. Okay. Well, look, it is well past the hour, and I think I'm going to close this up, and I'm going to stop sharing. It means I'm going to have to sit up again. Man, I get totally relaxed, just sort of, slouching around, looking at things, and then I've got to pop back onto the screen and actually look somewhat presentable. Somebody's got to do it. Cheers. All right. I think for now I'm going to get out of here. I think we had a good show. I'm you know I'm going to say this every single time. I like the format of sort of a daily show because I I don't really feel as though I have to be exactly right and completely you know try to cover all things. Um, Scientists make a lot of mistakes, and we don't have all the answers or um, uh, all the explanations. And I don't think it's necessarily fair, to put a scientist on the spot, um, trying, to answer um, um, questions about things. I think that puts a lot of pressure on them and sort of um, 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 elevates them, to be sort of a high priest, which none of us are. None of us are. We're all as confused as um, um, everyone else, and but we have a process to try not to be confused, and that's an ongoing thing. It's an ongoing thing. So yeah, having a daily thing like this, uh, where I can just get better all the time. That's very, very awesome. All right, I am worn out. It's been a lazy, lazy, lazy day. Hardly done anything at all. Just sort of not done anything today. So I am worn out. I'm worn out. So I'm going to get out of here because I definitely respect your time. I appreciate you coming in live. I also appreciate those who are going to watch this later. Um, so if you haven't already, make sure to subscribe and hit the notification. And let's see, hit the thumbs up or the thumbs down. I don't really care. I'm interested in the absolute value of your response, and not necessarily if it's a negative or um, uh, positive. So make sure to share this as well. Spread the word. Definitely want to get a nice big crowd in here. Uh, have some interesting conversations, right? Very, very awesome. All right, I think I'm going to get out of here because, as I said, man, it's just been a rough day, rough day, rough. All right, so I'm going to get out of here. Peace out. I will see you again in less than 23 hours. Less than 23 hours. That's like less than one rotation on the axis of the Earth. Less than one of those, and we'll be back again. So come on back. And all right, I'm going to get out of here. Peace, cheers, and all of that. See you tomorrow.